Okay, so this problem is a kinematics problem. And we've got a car. I'm not a great artist, but this car is traveling to the right here at 75 kilometers per hour. And unfortunately, there is a red light. Well, let's try and do that properly. There you go. There's a red light exactly 30 meters away. And at that point in time, the driver slams on the brakes, and the acceleration of the car, therefore, is a negative 6 meters per second squared. That's the maximum deceleration that the car can produce. And that's actually pretty reasonable. I mean, if you think about it, if the car was able to do 9.8, then you would be able to impose the force of gravity horizontally on the car from the brakes. That would actually mean that the coefficient of friction would be equal to 1, so that's too high. So therefore, 6 is actually pretty good. I don't think you'd be able to get 6 in the rain. So this is a pretty good stopping car. Now, the next piece of information that we need to figure out is basically, is the car going to make it? Now let's see, what are we given? Well, in terms of what we're given delta D is 30 meters, but that's a question mark because it actually might take longer to stop than that. What else are we given? Well, we're given that the initial velocity is in fact equal to 75 kilometers per hour. If you'll notice, I'm mixing units. So this unit here is kilometer per hour, and this unit here is meters, and this one is meters per second squared. The smart thing to do here would be to convert this one into a meters per second. And the way we're going to do that is we're simply going to divide by 3.6. That's the quick way to convert. So if you go 75 divided by 3.6, you're going to get, and if you're wondering how I know how to divide, remember the kilometer per hour number is bigger, always bigger, so therefore the meter per second number has to be smaller, so I'm going to divide. So we go 75, enter, 3.6 divided by, and we're going to get 20.8 meters per second. Now, we can actually write that down here, 20.8 meters per second. And now, there's another piece of information which we haven't really specified directly, but it is implied. And that is that the final velocity must be equal to 0. Okay? Now the question is, which equation could we possibly use? And let's have a look at this equation. V final squared equals V initial squared plus 2a delta D. Because what we want to find is the delta D if it is in fact less than or greater than 30. Then we'll know if he makes it to is able to stop before the red light. So in order to solve for delta D here, we just have to do a little bit of algebra. We'll go V final squared minus V initial squared divided by 2a is going to equal delta D. Now we're going to go ahead and put our numbers in. Now we know that V final squared is 0. V initial is 20.8. So we're going to go negative 20.8. And that negative is here. Okay. Meters per second squared. So we putting in 0 for the final velocity. And then we're going to go 2 times negative 6 meters per second squared. And now for delta D, let's plug this through our calculator. Now if you'll notice one thing, this negative ends up canceling this negative. So let's square this and where's my square here? Here we go. And then 2 divided by, and 6 divided by, and we get an answer of 36.17 meters. And in fact, therefore, the car is not going to be able to make it to be able to stop in the allotted 30 meters. The car is going to go for another 6.17. The car is still going to go for another 6.17 meters past the red light, and therefore they might end up crashing, and that's not good. So there you go. That's the end of this problem. Hope you enjoyed it.